But before that, let's come back to this, let's come back to this particular subtle point here where we put a clock bar in the register file. Okay, so this is a little bit tricky here, okay, because what we are saying is that you are trying to read a register out, okay, but you're trying to read a register out through a combinational path through the register file, and that gets captured by flip-flop 2 on the positive edge, but the write is going to happen in the negative edge. So therefore, if the register file needs to be used in the same clock cycle for read and for write, then the only way we said was you do the write in the negative half of the clock cycle, but you do the read appropriately in the next half, right? So this is that's why we put that clock bar, and therefore I have to ensure that this T register file read plus T setup and all happens within half a clock cycle, okay, and I don't have to worry about T PCQ because really the register read is happening in this sort of the later half of the clock cycle, right, and therefore this TPCQ is not going to affect that part of my clock cycle because TPCQ happens only here, right? But what we are talking about is the register read is sort of going to happen around this path. The write has to complete the register write has to happen here, register read has to happen here when the clock goes high, right? So the register write back has to happen in this clock cycle, and therefore I don't need to worry about this. However, T RF read plus T setup has to happen within half a clock cycle. Okay, so therefore I do a multiplication by 2 there, right? Now I am going to come to the execute unit, but I'll come to that a little later, okay, and I will look at the demem part before that. What is the demem part? If you look at it, flip-flop 3 is going to capture that data, right, and flip-flop 3 is going to launch the data and flip-flop 4 is going to capture that data for you, right? So therefore, if you look at, okay, what is the critical path, what is going to happen and all that, then we are simply looking at the data coming out of this, right? All of these signals come TPCQ later, right? So everything comes TPCQ after the clock edge, right? Then you go through the data memory you are trying to read, and therefore the critical path will simply be this. You have to do TPCQ, then the address is given to the data memory, tmem, and then T setup. So that looks very similar to my earlier delay for fetch, tmem plus T setup. Okay. Now what do I want to do? The last stage, which is my register write back stage, right? I want to do my register write back stage. So let me just add that just one line below, register write back. So here you are trying to launch on flip-flop 4, right? And then you are going through a mux, right? And then you are trying to come back. So if you look at this, there are multiple paths that are possible here, okay? And technically, remember, just like in the fetch stage, we had 2 capture flops. One was the program counter itself, the other was FF1. Now, one of these 2 will end up being the critical flip-flop that's going to capture, right? And therefore, we will consider that as a critical path. But the fact is, there are many different delays that are involved here, right? So therefore, if you look at this, I can start here, you go through the mux, right? The data can come all the way like this to my WD3, because you are trying to write back to that register. Okay, and now what do we know? We also know that this write back has to happen on the negative clock, and therefore this whole operation of T mux, so this is a T mux delay, right? And you have to come and write back into the register, right? So that operation has to finish within half a clock cycle, right? So again, if you look at this, I will say this is my the capture flop is my register file, and my delay here is again 2 times TRF write or TRF setup. That's what we needed, right? Right, plus T mux. Right, you are going to come out of the T mux, you are going to come back and then write back into the register file. Of course, remember the same, there are multiple paths now which are all, that this result W can go through different paths now. So if you look at this result W is actually nicely going through like this. There is one path here, one here, one here, and all that. Okay, so if you look at this, technically in one clock cycle, right, the same clock cycle, my FF2 could launch some data in this path, but FF4 could go through a multiplexer and come back. So this technically does not belong to the write back stage, critical path. Okay, so if you look at this, the write back critical path, we will just say it is 2 into RF setup plus T mux. Okay, that's all we are going to call it there. And so we can come back here like this and take a look at this. If you look at this, yeah. However, okay, so now the only problem here is you have to include this TPCQ, because remember, data is being launched by FF4 on the rising edge, right? And then this particular data signal, right, all these signals are available only after TPCQ. Then you go through the T mux, then you have to set up this thing, and that has to happen within half a clock cycle. So therefore I will say TPCQ plus TRF setup. Okay, that TPCQ was not there for this decode stage, because really we were in the second half of the clock cycle where TPCQ does not appear technically. Okay, so now the last part of our critical path, right, discussion is the execute block, and therefore we need to figure out what is the critical path for this, right? And this is not going to be so trivial, so therefore what I will do is this alone I will put it as a separate block diagram here that we can discuss. Okay, so the way to analyze this block, right, is of course you first identify the capture flop, right? So this is FF3, FF4 and FF2, FF1, okay, different flip-flops. So now if you look at it, right, there is all the FF2 data will be available TPCQ after the clock edge, right? All the control signals, right, all this control signal, this data, everything will be available TPCQ later. Now you are going to go through a mux here and so on, and ultimately the ALU is obviously, we know that takes a very long time, right, about 120 picoseconds. Therefore, what we need to do is we are going to look at the delays associated at the input of the ALU. Okay, the input of the ALU, okay, is going to come from different things. One is this control signal, the other is this source A and source B. Okay, the control signal is going to be available at what point? It will be TPCQ. Because as soon as the clock edge goes high, that TPCQ, it will be available at that point. Now source A, right, is going to come. If you look at the arrival time at source A, it is basically going to involve the delay of this mux, right? And then you have to look at the arrival times at the three inputs of this multiplexer for 0, 0, 0, 1, 1, 0. What are the arrival times? Here the arrival time will be TPCQ, right? Then there is a 0, 1 input. Where is that coming from? That is coming from here. So the flip-flop 4 clock edge is going high, you are launching something, then that read data W will take TPCQ, then you will go through a Tmux delay, result W therefore will be ready after TPCQ plus Tmux of the clock edge. You come back all the way and then the input to the multiplexer there will be ready after that much of delay, right? Then there is a second path here, right? What is the second path? I have to look at this. So if you look at this delay, I am talking of this particular delay here. This will be TPCQ plus Tmux. Okay, this is one Tmux, then this is another Tmux, right? So therefore, I am talking of TPCQ plus Tmux is when the 0, 1 input of this multiplexer will be ready. So this will be the arrival time. Now for the 1, 0 stage, what is my path? You just trace this path here. And this is coming straight from the output of a flip-flop. Therefore, this arrival time to the mux will be TPCQ, right? So, therefore, if you look at the arrival time of the source A signal here, this will be TPCQ, okay, max of the arrival times of the three inputs, which is TPCQ, TPCQ plus Tmux and TPCQ. So, it will be TPCQ plus Tmux plus another Tmux. Okay, so the ALU input is going to arrive, source A will arrive after this much time from the clock edge. Now you look at source B, okay, we are doing a similar thing. This select line, okay, is going to appear after TPCQ delay, right? So we are assuming that the forward A and forward B and all have that is just a simple OR gate and all that, right? So it will be a very small delay compared to these things. So we are not worrying about that control signal right now, okay? So if you look at the source B, there is a multiplexer in that path, right? So therefore let me mark that one with a different color. Maybe I'll use green now, right? So if you look at this one is, I have one arrival from here and I have one more arrival from here. So where is this coming from? It is coming from here. So this EXT IMME is going to be available TPCQ after this. So this guy out here will be just TPCQ delay, right? And on the other hand, this guy is the output of another multiplexer. Now what are the inputs for this? Again, that is going to come from this input. Arrival will be TPCQ, okay, because it's coming straight from a flip-flop. Then the other one is coming from the same magenta line, which is TPCQ plus Tmux, right? Now, and the 1, 0 is coming again from a very similar thing, which is TPCQ, okay? So therefore, if you look at this source B signal here, right, it is basically very similar to the earlier one. So I have TPCQ plus T mux plus T mux, right? So this was one mux, this was one mux. Now I have another mux, so I'll put another mux there. So the ALU source A and source B are arriving at different times, and therefore what I need to now worry about is the maximum arrival time, which is the source B, right? And therefore the delay now is going to be incremented further by the TALU time, right? So if you look at this, I am going to now go through this TALU, okay? Now the TALU output goes directly to flip-flop 3, okay? So technically you would think that is the critical path, but note that there is a 0 flag here which is coming out, right? So therefore if you trace this particular path, something very interesting happens. You are going through this logic and or logic, coming back here through this mux back to the PC, okay? So the ALU output would have been ready after this much delay, TPCQ, T mux plus 3 T mux plus TALU, right? That would have been ready. However, you also have an additional AND OR logic plus one more multiplexer delay, and the capture flop therefore now happens to be the program counter, okay? And this is obviously going to launch from FF2, right? Or FF3 actually, FF4, I'm sorry. It could come from FF4 also. So if you look at the capture, the critical path, who is launching this data? Actually it is going to be the FF4. It is not FF4, okay? So starting from that point, okay, you go all the way around back to the program counter, okay? And that's why you look at the critical path here, which is marked in red. You start from this flip-flop, okay? You start from this flip-flop, go all the way around through this guy, in through one mux, two mux, and of course there is already a mux there, through the ALU, 0 flag, come back here, AND OR gate, come back through another mux to the program counter. That is the critical path of this particular execute stage, okay? So it can be tricky for us to figure out what the critical path is, and therefore if I now go ahead and summarize this whole thing, the critical path for this particular stage will be TPCQ, okay, plus 1, 2, 3, 4 muxes, okay, plus 4 T mux, okay, plus ALU delay, plus the AND OR gate here. And of course you have to set up appropriately before, right? So therefore if you want to write this down specifically, it would be critical path, right, is going to be TPCQ plus 4T mux plus TALU plus T AND OR plus T setup. That is going to determine, okay? Therefore, in summary, what you find is, if I put all of this together, the pipelined clock frequency or the clock period is going to be the maximum of the critical path delays for each of these stages, which is exactly what we have shown here, right? TRF write, twice TPCQ plus T mux plus TRF write for the write back, TPCQ T mum T setup for memory, data memory, right? TPCQ for T mux TALU T AND OR plus T setup for execute. Decode, it's very similar to write back except that there is no TPCQ, right? 2 RF read plus T setup. finally the fetch is again very similar to the data memory read. It is T PCQ, T mem and T setup, and therefore based on the values that we have chosen, clearly this guy is the guy that's going to determine the critical path, and therefore I can calculate the pipelined clock frequency for this as, you know, T PCQ of a flip flop, right, which we are assuming is about 40 plus 4 into T mux 120, ALU again is 120, and OR gate 20 plus a T setup of the flip flop, right, which is 50. Okay, so therefore we are talking about a clock frequency of about 240, 350 picoseconds. Okay. So based on this, if I take the 100 billion instructions with the CPI that we just calculated, which is 1.23, right, you do 100 billion instructions. So remember that when we looked at the CPI for this you know, set of instructions here, what is the average CPI and stuff like that, we basically said we found that answer to be 1.23, right. So let me just go back to that. We are talking about CPI of 1.23. So we have to look at this. We got a CPI of 1.23 and we plug that in out here, right. So if you look at this, you get 350 picoseconds, 100 billion instructions into 1.23, 350, you get 43 seconds as the answer, okay, for the pipeline processor. So comparing the performance of the same benchmark on 3 different processors, single cycle, multi-cycle, pipeline processor, it turned out for that distribution of instructions, right, the single cycle gave us program execution of time of 75 seconds, multi-cycle went up to 155. Why? Because you are now actually 52% were, you know, R type, right, whereas and the cycles per instruction therefore on average went up significantly at that point, right. So and therefore that took 155 seconds, which means that the multi-cycle was inferior for this particular benchmark, but the pipeline processor on the other hand took 43 seconds, and therefore the relative speed up, assuming that the single cycle you know, cycle program execution time is considered normalized to the single cycles program execution time, the speed up would be 1.5 and 1.7. Therefore, the pipeline processor is indeed the right way to go forward in terms of implementation and usage. Thank you.